Hello and welcome to lesson 6. In lesson 5, we looked at what are called fundamental particles. And fundamental particles are particles that cannot be broken down into anything smaller. So that was seen in electron-electron collisions. In other words, two electrons going against each other. Now, what happens if we try and break up some of our bigger natural particles, protons and neutrons? Well, the theory suggested that protons and neutrons were actually not fundamental. The theory is actually very complicated and is beyond anything in higher or advanced higher, and has a grounding in quantum mechanics, which is really quite difficult maths for university level. So we're just going to look at what actually happened in theory. A lot of this is, again, written information. You'll have seen over the last few lessons that there's no calculations really at all. And it's all writing, and it's stuff you've got to write down in notes as we go through these lessons. You can obviously pause these lessons. If you're having trouble pausing the lesson and getting up to date with the notes, try downloading the lesson. Downloaded lessons are usually a little bit easier to pause and restart, a little bit easier than live streaming. There's also notes at the end, very similar to some of the other lessons, where you can have a look at those and top up your notes, or you can wait till you do the whole thing, my lesson plus the notes at the end. Okay, so electron-electron collisions, fundamental particles. Let's have a look at what happens if you fire an electron at a proton. So the theory suggested that protons weren't fundamental, electron is, and in practice, in experiments, electrons were fired at protons, and this was first carried out in something called the Stanford Linear Accelerator, SLAC or SLAC. We'll be doing much more about the different types of accelerators and how they work later on in this section. And as usual, if I write something down, it's probably a good idea for you to get it written down. So we've got the SLAC, Stanford. Linear accelerator, where an electron was fired at a proton. The electrons started off at one end of the accelerator, and they were accelerated down a very, very long pipe. I think, if I remember rightly, it's a couple of kilometers long, very, very long straight pipe. Most modern accelerators are circular, like the one at CERN in France, but this is a linear accelerator. So electron starts off at one end, it's not moving, and it's accelerated down a long, long pipe and is smashed into a stationary proton. And the experiments found that the deflections, this is a little bit like Rutherford's experiment, when alpha particles were fired into the nucleus of an atom, that some of the deflections came back at an angle, or they perhaps whizzed off at an angle. So the theory suggested that this proton is actually not a fundamental particle. It's made up of smaller particles, because the advanced maths says that you should not be able to get the type of deflections from a fundamental particle as you do as if this was made up of a number of small particles. So we've got a high energy electron accelerated into a stationary proton. And we needed a name, physicists needed a name for these smaller particles that made up a proton, and these particles are called quarks. And quark is a made-up word, and it's taken from a book which title is Ulysses, written by the Irish novelist James Joyce. So quarks, we think it's quarks because it's pronounced quarks as opposed to quarks. Quarks because in the book it's written down that quark, this made-up word, rhymed with Mark. You don't really need to know that, but you won't obviously be tested on your pronunciation in any test, but it is pronounced quark. Okay, so firing electron goes down, splits a proton up into quarks, and we believe now that quarks are fundamental, and further experiments where physicists have tried to break up quarks have been unsuccessful. So quarks, which make up protons, are themselves fundamental. And remember, fundamental means that you can't break up the particle into smaller parts. So it was found that there were two matter particles, and these were named up, the up quark and the down quark. Now, if you cast your mind back to when we looked at the family of particles called the leptons, we start off with an electron and a positron, and that's just two particles. But by the time we've finished, we end up with many more. And we're going to make up a table, and we're going to talk about all the different quarks, or the more fundamental particles that make up protons and indeed neutrons, and we'll come on to that in a minute. So we're going to make up a table. I'm going to do my table down here. You might want to leave a bigger space for making up your table, and we can add to the table as I go through. So I've got an up quark, and I've got a down quark. Now remember, every matter particle has an antimatter equivalent. So we've got an anti-up and an anti-down. And these, just as we did with electrons, these are low energy. They're sort of normally occurring particles that make up things that we commonly find around us. So these here, the up quark and the down quark, are low energy in our low energy world that we live on, and they go to make up protons and neutrons. If we do these collisions at a much higher speed with much more energy, we get the particles splitting up into more massive versions, heavier versions of the up and down quark, which just are the same as the up quark and down quark, but they are just larger with more mass. And so this is like the family one, if you like. It's our commonly found particles. More energy gives us family 2 and gives us more massive versions. So they're just exactly the same as the up quark and the down quark, but they're bigger. And the heavier version of the up quark is called a charm quark, with the letter C, and its equivalent across here is called the strange quark, symbol S. And of course they have antimatter equivalents, the anti-charm and the anti-strange. That's family 2. And then family 3, what's family 3? Well, family 3 is just the same again, but with higher energy collisions. E equals mc squared, bigger E, bigger M, more massive versions of these. And family 3 is called the top quark and the bottom quark. And of course, we've got their antimatter equivalents, which is anti-top and anti-bottom. So we've got a table here, 2, 4, 6, 8, 10, 12. 12, you'll see a certain amount of symmetry in this with the lepton family. And this is obviously called the quark family. So these are all quarks. And we can say that these are sort of low energy, and energy gets higher as we get down to higher energy down here. And we can put these in a table like that. So that's our family, the quark family, a sort of fundamental equivalent to the lepton family. Okay, so what we can do then is we need to find out and remember what combination of quarks actually go into a proton and what combination of quarks go into a neutron, and that will be my next page. So I'm just going to leave that down there. So all of these are fundamental particles. Okay, so let's have a look at a proton. Now we know a proton has a charge, and it has a charge of plus 1.6 times 10 to the negative 19 coulombs, sometimes just called plus 1. We've got our electron, has a charge of minus 1.6 times 10 to the negative 19 coulombs, sometimes just called minus 1. And we know that a neutron has 0 charge. So these are relative to each other. Now, if we're going to take a proton and we're going to split it up into smaller bits, each of the smaller bits must have a charge that when you add up the charges on your individual components, they come back to plus 1.6 times 10 to the negative 19, or relatively speaking, plus 1. Now remember, an electron is not made of quarks, but I just put the charges in there so you could see. If we're going to split up a neutron by firing electrons, high-speed electrons at a neutron, we're going to split up a charge of nothing into smaller bits, which when you add up the charge on every smaller component part of the neutron, then the overall total charge adds up to 0. So first of all, we'll look at the proton in more detail. And a proton's got a charge of plus 1. And physicists reckon that a proton is made of 3 quarks, 3 subcomponents. So it's in fact made of 2 up quarks and 1 down. So a proton's actually made up of 3 particles altogether. And when you stick them together, that's what you get with a proton. So I'm going to draw a picture, if you like, of my proton. And it's made itself of an up and another up and a down. It's not supposed to be a funny face, but it sort of comes out like it. Now these, and again, we'll be doing this, there's a lot of this, we'll be doing this later on stuff. These 3 components are held together with some forces, and we'll be looking at the forces that go into our standard model that hold these particles together. We'll be looking at that in another lesson. So I've got 2 up quarks and 1 down quark. Now, how do the charges work out? Well, an up quark has a charge of plus 2/3. It's part of 2/3 worth of 1.6 times 10 to the negative 19. You need to remember this plus 2/3 bit, but you don't ever, I've never seen a question where you actually take the charge, the 1.6 times 10 to the negative 19, and divide it up into 2/3 bits. So we just work with the relative charges. And the down quark has a charge negative 1/3. So we're going to take 2 ups and 1 down. So in effect, a proton is up, up, down, the 3 of them. We've got plus 2/3, and we've got another plus 2/3 for the second up quark, and we've got the down quark has a fractional charge of negative 1/3, and when we add these together, we've got plus 2 is plus 4, minus 1 is plus 3/3, and that is equal to plus 1. So that's how the proton has an overall charge of plus 1, by taking your fractions of 1.6 times 10 to the negative 19 and divide them into smaller bits. Okay. So that's the proton, made up of a combination of ups and downs. So our normal everyday matter particles are low energy stuff, and we're made up of electrons, which is a lepton, and protons, which is made up of quarks. In this case, 3 quarks. We'll come back to look at a proton and its 3 quark components later on. Let's have a look now at a neutron. Now, a neutron is not a fundamental particle, just like a proton is not a fundamental particle, and it has 0 charge overall. And here's a picture of a neutron. And a neutron, like a proton, is also made up of 3 particles. And it's made of 2 down quarks and 1 up. So I've got a down, and an up. Now, you'll remember that a down quark has a charge of negative 2/3. So I've got 2 of them. I've got 1 of them, and then I've got another one, and then I'm going to add an up. Like that. No, that's not right. That's completely wrong. Completely wrong. My down quark has got minus 1/3, and there's 2 of them. That's why I was hesitating. I thought that's not right. And my up quark is plus 2/3. I'm sorry about that. Hope you didn't write that down in ink. Okay, 2 downs and an up. Down, down, up. Now we add those together. Minus 1, plus 2. And you add that up together and you end up with no thirds. You just end up with 0. Apologies for that. I can't remember myself. You got to remember this. You got to remember the downs have minus 1/3 and an up's got plus 2/3, and a neutron is made of 2 downs and up. And again, these quarks are bound together inside the nucleus with some sort of force. More on forces later. Okay, so our 3 main particles then: electron, fundamental in itself, is a lepton. Our proton and our neutron are not fundamental. They're made up of quarks, which are fundamental, and these have fractional charges, and they join together to give the charges that we know of and are very familiar with. Right, So who's to say we couldn't have a particle of just one quark? Well, actually, one quark, these quarks are pretty unstable and only become more stable when they join together in groups. And one quark is never found on its own. Numbers of quarks you can join together. So never found. You never find a single quark on its own. These are so-called naked quarks. It's hard enough to see quarks in groups, let alone actually see them on their own. So we've got, what's the next? Numbers of quarks, 1. What could we have? We could have 2. We could have groups of 2 quarks. Quarks will live in groups together, never on their own. But if you're going to have 2, physicists have found that you only have a particle grouping of 2 quarks, which is made up of a quark and an antiquark. So 2 quarks, a quark and an antiquark pair. Particles that are made of 2 quarks, a quark and an antiquark, can't spell, quark and an antiquark pair are called mesons. So I can take any quark. I could take an up quark and an anti-quark. I could take an anti-up, or I could take an up quark and an anti-charm, or I could take a top and an anti-down. And once you work through all these different combinations, you get lots and lots of mesons. Now, what happens? Because it's a quark and an anti-quark pair, that's matter and antimatter. And almost as soon as they combine, then they annihilate each other. You'll remember this, matter and antimatter, they annihilate. And so they are very, very short-lived, and they don't hang about too long. Now, a good way to remember that a quark and antiquark pair is called a meson is if we take the word me and we take another bit son, meson, we've got 2 syllables. So our 2 quarks together form something called a meson, and it's 2 syllables, and it's always a quark and an antiquark pair. A common quark-antiquark pair is a pion, and pions have a symbol, funnily enough, pi. And of course, wherever there is a matter particle, there's an antimatter particle. So you can get a matter particle and you can get an antimatter particle, or a pi with a bar. But you don't really need to know all these, but there's a whole range of them, and they've all got names and they've all got symbols. Okay, so moving on, numbers of quarks. What we've done 1, which you don't find on their own. They don't exist on their own. You can have a quark or an antiquark pair called a meson, but they are short-lived. They're pretty unstable. Let's go on now to what happens if you have 3 quarks together. And this is our proton and our neutron. There's the neutron there. There are 3 quarks joined together. And we always find them in threes. They're either 3 matter particles or 3 antimatter particles, 3 matter quarks or 3 antimatter quarks. They don't pair up in threes across the matter antimatter grouping. So obviously we've got our proton, 2 ups and a down. We've got our neutrons, 2 downs and an up. Now these mesons, very short-lived because they are quark-antiquark pairs and they annihilate. But when you get matter quarks together, they're quite long-lived. And as far as we know, physicists have been able to work out how long they think that up and down a proton, how long does a proton exist? Well, at the moment, we think a proton has a life of something like 10 to the power of 34 years. So a proton is pretty stable. Electrons are pretty long-lived as well. Neutrons on their own don't actually last very long at all. They've got a half-life of about 10 minutes. So after 10 minutes, if you have a neutron just sitting there on the table all on its own, after about 10 minutes, half of the neutrons have all decayed into something else. But as soon as you pair up neutrons and protons together to make a nucleus, they become also very, very long-lived. So we've got 3 quarks or 3 antiquarks. And when we have 3 of these together, they're called baryons. And an easy way of remembering this is that baryon, ba-ry-on, is 3 syllables, 3 syllables, baryon, and that will tell you that it's made up of 3 particles, 3 of our fundamental particles, and that's all you really need to know. You probably don't even need to know that you can't get naked quarks, single quarks on their own, but you definitely for higher need to know that 2 make a pairing called a meson. It's a quark and an antiquark. You definitely need to know this, that 3 together make a baryon. Of course, if you extend that, and again, this is not higher, we could get 4 quarks together, and 4 quarks are called tetraquarks. Don't know where tetra comes from. 5 quarks together, pentaquarks. No idea where penta comes from. Just saying that. Of course we do. And these are more of what are called exotic particles. Some of these particles were only discovered sort of 10 or 15 years ago, but the ones you need to know the names of and what they comprise are the ones of 2s and the ones of 3s, and the other ones we don't really need to know about, but I'm just sticking them in there for just a little bit of interest. All of these groupings of quarks, mesons and baryons, whether it's tetraquarks or pentaquarks, are all grouped together in a sort of much bigger group called hadrons. So what are hadrons? A hadron is a composite particle made of 2 or more quarks. 2 quarks, 3 quarks, 4 quarks, 5 quarks. These are all called hadrons. Okay. Later on, we'll be putting all of these names together, hadrons, mesons, baryons, leptons. We'll be sticking the whole lot together in a big sort of overall plan. And the overall plan, including all the forces that hold things together, that's actually what is called the Standard Model. So the Standard Model is our complete understanding of everything that makes up everything in some sort of intelligible large plan together. So that's why it's called, I don't know why it's called the Standard Model, but the Standard Model is actually all of these things listed out together. And we're just doing little groups. Okay, one last thing about charges. I've rubbed that table out there, but I'm just going to redo that slightly bigger. Up, down, anti-up, anti-down, charm, strange, anti-strange, anti-charm, anti-strange, top, bottom, anti-top, anti-bottom. There's our 12. Nice and symmetrical. Right, all of these particles, although this is the lightest and smallest and is sort of low energy, remember family 1, low energy, family 2, higher energy, family 3, biggest amount of energy. And I suppose there's a question, if you can get even bigger and bigger and bigger, large amounts of energy, are there any others down here? Well, we don't know. And the Standard Model is still still evolving. It's not a finished thing. But all of these, small mass, medium mass, heavy mass, all of these in this first column have a charge of plus 2/3. And the only difference is that this is small mass, medium mass, heavy mass. All of these ones in this column have a charge of negative 1/3. Now, that's the particles, or the mass, the ones with matter, and these are our anti-particles, or our anti-matter. And the whole definition, you'll have to go back a few lessons for this, the whole definition of particles and antiparticles is that they have the opposite charge. You remember, an electron has a single negative charge, and a positron or anti-electron has a single positive charge. So you have to take the charges on your particles here and just change them to negative. So all of the particles in this column have a charge of negative 2/3, and all of the ones here have a charge of plus 1/3. Okay, and that finishes this next lesson. This lesson, which was, I just need to check back, this was lesson 6. And we are still building up our standard model, and the next bit will come in lesson 7. Now remember, it will be an assignment anyway. Remember that you are going to have to make your own notes and commit all this to memory as part of your assignment. And I will finish this lesson right here. Thank you.